Terry. It's a pleasure to be here, a pleasure to be at Stanford as well. And I have two goals with my talk today. The first was to try and give a historical overview of data visualization, an area that's clearly near and dear to my heart. And then in the second half of the talk, I'm going to talk about what I see as some of current trends and research areas that I hope to engage in now that I'm here at Stanford. And so I'd like to start the talk with a question for you. What do you think was the first data visualization? Any thoughts?
Probably carbon clay tablets.
So Terry said probably carbon clay tablets. Yeah. What's that? Hieroglyphs?
Numbers of buffaloes on cable.
So yeah, buffaloes on cable. So certainly there's pictorial representations, and so we might get into an issue of definition of what we mean by data visualization. But typically we talk about different ways that are representing some form of collected data out in the world. Typically representations that help us make decisions or navigate in the real world. And so, well, perhaps a contentious pick. This is what I settled on and what I could find, at least as the oldest recorded example of a data visualization. This is a town map from the city of Konya in modern-day Turkey, and this originated from about 6200 BC. And so here you see a representation of, basically different abodes in a street structure that might represent and perhaps help navigate or delineate property lines, etc., for this, now ancient community. Now, maps, of course, not surprisingly, one of the first representations to become common as navigation in the world is a task we've been dealing with for millennia. And so I'll quickly jump ahead over 6,000 years to see another example. And see, again, mapping still one of the most common things. This is from the Ptolemy's Geographica. And what's interesting about this map is, one, it represents a spherical Earth, and it's actually the first to use longitude. But one of the things that's really interesting about this map is, one, while latitude is measured from the equator as we normally know it, Ptolemy actually thought about it completely different. So rather than measuring it in degrees or arcs, he actually measured it in time, given, say, an equinox, how long is the sunny day. And so he actually used thoughts of time, in this case, in his spatial representation of maps. The other thing about this particular graphic that I find particularly fascinating is that it's actually had a very long life. So this is actually a living document that was very influential throughout the Middle Ages. And at the end of the Geographica, there were a number of topographical tables that were actually extended by scholars throughout the millennia. So in this way, this document actually grew after Ptolemy's time, a sort of proto-Wikipedia, if you will. And so I will continue to move along at lightning speed here. We'll jump ahead another 800 years, where we see one of the first instances of plotting or graphing. In this case, the first time series visualization. Some of you might recognize this from the works of Edward Tufte in his books. But here, we have like the dawn of science, where people are actually making measurements, in this case, using visual representations to record and then analyze those measurements. In this case, the movement of heavenly bodies across the sky over time. Moving forward again, we get into something I find particularly interesting and surprising visualization for me. This is the work of the French philosopher Nicolas Oresme, who back in the 1400s was one of the first to start using graphical representations to map abstract mathematical functions. So now what's interesting here is he had the idea of taking data, but in this case, mathematical functions, and representing them and plotting them in a two-dimensional space. And why this is interesting is this is actually laying the foundations of analytic geometry over 200 years before Descartes. So I was a bit surprised to find both that it predated Descartes by that much, and that he basically invented proto-bar charts back in this age. Moving forward again, we see that, again, science was driving a lot of visual representations, particularly throughout the Middle Ages. This is the work of Christoph Scheiner, who was a contemporary of Galileo. And Scheiner was looking through telescopes with colored lenses to track sunspots. He's actually considered the co-discoverer of sunspots along with Galileo. And in particular, in this case, he recorded for each telescopic view the positions of sunspots seen on the sun. In doing so, this becomes both a record of scientific observation and a means to analyze those data. And for those of you familiar with Tufte, you might be interested to know that this is actually the first example known of a technique called small multiples, by taking related plots and repeating them within iView so that you can then make quick comparisons between different plots of data. Shortly after that, we find what's considered to be the very first statistical graphic ever. This was done by the Dutch astronomer and scientist Van Langren, who then plotted on one graph different estimates of the longitudinal difference between the cities of Toledo and Rome. So if you look at the labels on the right here, you may recognize some famous people, including a measurement estimate by Mercator, inventor of the Mercator projection of the map. And you'll notice it is, interestingly enough, two clusters or so of observations made by these different scientists. And so basically taking the average of those clusters, Van Langren placed the label for Roma in between the two, kind of conveniently located there by the differences in estimates. Though perhaps unfortunate for the scientists of the time, they were all wrong. The actual measurement is here, and so due to bias of the measurement technologies of the day, actually all overshot the actual longitudinal difference between the cities. And so kind of rapidly we see how different visual representations were formed, again, often as a means of recording scientific measurement throughout kind of the dawn of the scientific era. And then from there, though, there was sort of a sea change as we moved away from scientists, particularly as hobbyists or people working under a system of patronage, to basically the rise of capitalism and also the rise of the bureaucratic state. And these two developments in human society resulted in a new wave of data. So people keeping track at a larger scale than ever before, commerce, inventory, the movement of funds, and also the administration of government, understanding the constituents of one's population. And so these results actually led to a need for new ways of representing and reasoning with all this data that was being created, and led to what I'll refer to as the golden age of data visualization, really an age of enhanced exploration and innovation. And so probably considered the father of statistical data graphics is the Scotsman William Playfair, who was the first to invent a number of modern statistical plotting techniques. In this case, the line chart. Here you see different trade data for England contrasted with imports and exports to Denmark and Norway. So you see two lines, so one the line of imports, and then below that at beginning the line of exports, and then the crossing. So you see the use of a line, in a rectangular grid over time to show change over time of these different quantities, and then coloring to show, in a nominal way, the balance against and the balance in favor of England over time. And this is just one of the many plots that Playfair invented. Another example is pie charts and circular charts. This particular example on the left here shows the makeup of the Turkish Empire in terms of geography. How much was in Asia, how much was in Africa, how much was in Europe at that time. And he didn't stop there. He also created other charts that tried to combine multiple measures within a single view. This was actually rated by The Economist as one of the 3 greatest statistical graphics of all time. We'll see the other 2 later. In this particular case, it graphs the change in wheat prices over time against the fluctuations in the wages for laborers. And plotted with those data along the top, though it may be hard to see, is actually the different reigns of kings and queens of England. So trying to create in a single view a means to compare these different data series. And in this case, you'll find that prices in wheat and workers' wages tend to fluctuate. This was an early argument of trying to understand how the forces of capitalism were actually affecting the working class, and whether or not they, their labor would keep up with the price of food needed to sustain themselves. At the same time, we start to see other developments in statistical graphical presentation. This is actually by the first modern statistical map done by the Frenchman Pierre-Charles Dupin. In this case, it shows rates of illiteracy across France. So you see that in the region of Paris, literacy was quite high, but then as you move away, you'll see different distributions of literacy, and in the center, a particularly low rate of reading. This then leads us to, I think, one of the more interesting examples I'd like to share with you today. This is a graphic of deaths in the Crimean War that was created by Florence Nightingale. And why this is interesting is it's an early piece of visual rhetoric. So first let me help you figure out what's going on in this chart. So this looks at first glance like a type of a radial bar chart. So you see that each sector here, which represents a month, is broken up into equiangular regions. And in this case, what they're showing is not the radius of the chart, but the actual entire area shows the number of deaths. And here it's subdivided by a number of covariates. So in blue, we see the number of deaths due to treatable diseases. In red, the number of deaths due to war injuries. And then in black, all other causes. And so this graph has led to a number of arguments. So some argue this is actually a very poor way to encode data, that it might mislead. So you might mistake, for example, radius instead of area as being the measure. And in addition, for those of you who are familiar with stacked charts, this actually is not stacked. So in this case, the blue represents area from the center of the circle out to the periphery. So in this case, the black and the red are actually layered on top of the blue. And all of this, though, was not necessarily what Florence Nightingale was concerned with. She wanted to represent the data accurately, but more importantly, she wanted to impress upon, for example, the royalty of England, the necessity for getting better medical treatment for soldiers. She wanted to show in which that was a graphically evocative way how deaths were occurring in the Crimean War. And as a result, she named this the coxcomb, which actually comes from the name of the crest on the head of a rooster. So already she was trying to be evocative in terms of her metaphors. And she stated this quite clearly, that she thought that the tables of figures that statisticians were collecting were not enough to either engage the public or to affect decision-making amongst the royalty. And so she claimed as her goal in this particular chart to affect through the eyes what we fail to convey to the public through their word-proof ears. And so basically, she wanted to make this evocative and different to try and draw people's attention in so they would actually get engaged with the data rather than, say, glaze when facts and figures were presented. And while her collaborator, the statistician Farr, who actually collected this data, argued that statistics should be the driest of all readings, clearly his contemporary Nightingale disagreed. And so moving on, in this same period, we saw the explosion of many different types of visual representation. So some of you may be familiar with the flow maps of Charles Minard, the French cartographer and graphic designer. In this case, it's showing the exports of coal out of England. So you can see, large movements of coal, both in terms of quantity and geographic travel. For example, from England into mainland Europe, around Africa, out to Asia, and then to the New World, particularly with a strong export of coal to the Caribbean. And you'll notice that as part of this design, Minard took great liberties with geography, letting the map change to accommodate the statistics as needed. The other thing I found interesting about this is an early example of what nowadays referred to as a multiple view or coordinated visualization. So up in the top right, we see an accompanying chart, which we can zoom on here, as a stacked graph that we see about 15 years of coal production in England. And what we see, first of all, is it moves from about 15 million tons to about 90, so it almost doubles in just the period of 15 years. In addition, all of those exports, interestingly enough, on that previous chart, make up only about 10% of all coal production in England, which means during the height of the Industrial Revolution, England is consuming 90% of all the coal that's being developed. Moving on to a couple years later, we have perhaps what's one of the best known charts of all time, which Tukey is referred to as the best statistical graphic ever made, though I think that's up for debate. This particular graphic shows the movement of Napoleon's armies and their Russian campaign and their subsequent dying off. So you see, we start from Poland, the army advances inward and then dies down in their approach on Moscow. And then you see the trickle of the army coming back as they return to Poland in retreat. And in this case, you see graphed along with it the temperature upon their return. And one of the reasons this graph is so widely heralded is because of its ability to show a number of different data variables simultaneously in a way that aids comparison. So in this case, we see both latitude and longitude presented, along with the size of the army, as well as its direction represented in color, then correlated with temperature. And so in this way, by using careful design, we can often elucidate many different aspects of a data set. And particularly in this day and age when it was required that these graphs be hand-drawn and that only static representations were available, particularly important to create a reference for understanding the data from as many perspectives as possible. Yes, Joy.
It's used mostly for marketing purposes to get more soldiers or food or what?
So there was a number of reasons. In the case of Nightingale, as I showed, that was really a type of visual rhetoric, where she's trying to convince someone to make a decision as she saw it. One of the interesting things, if you go back to Playfair, though, this is one of the first examples of really trying to get the data in a way that supports presentation. Again, this is being paid for, say, by royalty or by businessmen. And that way, I can actually consider what Playfair did, the kind of first instance of what today we refer to as dashboards, is, is like simplifying data down to a presentation that supports decision-making by some kind of executive. Yeah, Manu?
If you knew what's going on with that the brown line that's going up and connecting.
So there's different troop movements. And so each one of these branches are troops there. I'm not exactly sure why the troops went into North Poland there. I don't know what the campaign was. But they came back and seemed to suffer the least casualties of any particular branch. Yes, and then they all joined up on the return. So you see here, they all come together at the end, whereas these two separate branches come together right here as well. That's right. Yes?
Do you have a feeling of sort of the veracity of the underlying data? When you jigger, you can jigger the visualization.
Sure.
Maybe more easy to jigger the underlying data.
Right, and so Minard is actually a master of doing this. Often not to mislead, but as I showed you, like distorting geography is something he did regularly to sort of make the data fit more naturally on the display. Similarly, to make these paths, visually separate, I suspect he most likely jiggered latitude and longitude as well. Now, in terms of the actual troop size reports, the belief is that he did so faithfully. However, I don't know the backstory on how that data was collected and then made available to Minard. And so, without basically the historical document of provenance here, it is still open for argument. Should we believe what we see, even if the data is faithfully represented by the chart? There's always the question of where that data came from. Thank you. It's a great point. And so at the same time, these caught on. And so this is a picture from a French statistical atlas. And so at the end of the 1800s, you saw this explosion of these beautiful atlases used both to record the results of censuses and other data collection efforts by governments and businesses. And in this particular case, it shows the movement of rail passengers and tons of freight from the 4 different Paris rail stations out to the rest of France. And one of the things I find interesting about this is these atlases were, a feeding ground for innovation. And in particular, you see this here, this type of mosaic plot, where areas being used to represent different quantities. And for those of you familiar with tree maps, I would just note that this was made over 100 years before Schneiderman. And similarly, this you have not just in France, but in the United States as well. There was a number of atlases of the U.S. Census made. This particular graph shows movement between states. So the chart on the right shows emigration from a state, and the chart on the left shows where people moved. A couple of things are interesting here. With respect to the data itself, you see that New York was the most exited state in the Union, and then you see which states were growing most rapidly then. You see, Texas is among them. Illinois is a major one, I believe. I think Kansas was on here at some point. Yes, Kansas is a big one as well. And one of the techniques they used here was, rather than sort alphabetically, in this case, sort by the data to help reveal patterns more clearly. Something that's commonly done in modern statistical visualization packages today. And so, the takeaway from that section would be that there was a great deal of innovation in that period. Basically, as data became available and the need to make sense of it emerged, people responded by coming up with a number of really creative visual representations to aid reasoning and understanding of the data. And in doing so, came up with a number of forms which have subsequently been reinvented, whether it's in the field of InfoVis or elsewhere. So it's interesting to understand the historical record to know what types of representations were previously thought up. But after this period, around 1900, occurred something, basically a dark ages in visualization. So one is these beautiful statistical atlases I described died out for a number of reasons. But also innovation in the large in visualization came to a halt. And one of the main reasons for this was the rise of formal methods in statistics. So you had, Carl Pearson and then later Ronald Fisher really laying the foundations of formal statistics. So taking statistics, wedding it to probability theory, and coming up with the inferential statistics that we know today, including linear models such as linear regression, t-tests, etc., were invented during this period. And as a result, graphics were thought of by the statistical community increasingly as not robust enough or not reliable enough to tell the truth about data, and it fell into a bit of disfavor amongst the research community. And as a result, there was little innovation in graphical methods. Though I would say, the silver lining is that at this time it was also, though, a period of application and popularization. So that, at that time, though no new methods were being created, or at least were being created at a much smaller rate, techniques were being adopted into the curricula and being more often used in business. And so as a result, graphical methods did enter textbook and mainstream use. And so this created a setup for basically a renaissance of sorts in what I'll call the modern era of data visualization. And so the first thing I'll notice about this is from about the 1950s onwards, is one is the publication of a book, How to Lie with Statistics by Darrell Huff. And this is worth mentioning because it was still, I think to this day, the highest selling statistics book ever published. So it's sold over 1.5 million copies and has advice, things like not confusing mean with median, and also how different ways of plotting a chart could actually mislead or tell different stories. It's not that either is false, but they both give very different perspectives, and so often understanding all of those perspectives is important. But I would hope that if you've seen the Cartoon Guide to Statistics, it's also an excellent book, and I hope it gives Huff a run for his money. But perhaps the two most important figures in this era are the French cartographer and designer Jacques Bertin and the American statistician John Tukey, both of whom had basically fundamental effects in shaping how we think about data visualization and all the subsequent work that has been done in their wake. And this is largely enabled by a third development, which is, of course, the development of computational and display technologies. And it's really this kind of triumvirate of Bertin, Tukey, and the computer that really define what I'll call the modern age. And so I'd like to start with Jacques Bertin, who is a French cartographer and graphic designer, and is particularly well known for beginning or initiating the systematic study of visual encoding. And so he wrote a very influential book called The Semiology of Graphics, originally published in the French in 1967 and in an English translation in 1983. Unfortunately, it hasn't been republished yet, but if you have $200 or more, you can get a copy or visit my office, either way. But the great insight that Bertin had was really breaking down the space of visual and variable. So what visual means do we use to encode data, and how can we systematically study them? So here's an example of using position to encode information. And what are some of the basic perceptual tasks you can do? Well, first you can immediately see that points A, B, and C are not the same. They're distinguishable. So first, difference is an important characteristic. You can see that B is between A and C, so ordering. So understanding the ordering of variables is another type of pattern you might perceive. In this case, with position, you see that BC is about twice as long as AB. So you can get a perception of proportion. And so in this way, position as a visual encoding variable supports all three of these types of perceptual tasks. And so it's well suited to showing categorical data, rank orderings, as well as quantitative numbers. And this was put succinctly by Bertin as saying, like, there's basically three elementary perceptual tasks in the semiotics of graphics. And that's resemblance, order, and proportion are these three signified. So the three things that we perceive as we look at these graphics. And then we can use those to tie those to data and represent them more faithfully. And so in addition to this, he then tried to catalog the number of visual variables that were available. So this includes the top, you see position, so like position in X and Y or radially. Taille, which is size, value, which in this case means intensity of color. And then what he called, variables for separation that are less suited for quantitative data. So that includes grain or texture, which was particularly important given the printing technologies of their day. It was often easier to show textures than it was to do fine-grained differences in color saturation. Color hue as a way of distinguishing objects, orientation, and then shape. So we might tie data variables to these different visual representations in different ways. And Bertin then also sought to rank order them. So how good or how effective are these different visual encoding techniques for different types of data? And so in this case, it's actually ranked ordered by their ability to show quantitative data. But these orderings can change on whether we want to show ordered data or if we want to show categories. So for example, color hue does quite well at distinguishing categories as long as we don't have too many of them, usually within about 12 or less. And this led to other researchers to follow on and build upon Bertin's work put it on a more scientific footing. And my favorite person, who I consider a personal pioneer in this space, is the statistician Bill Cleveland, who at the time was at Bell Labs doing early work on what we now call graphical perception, as well as early interactive graphics. And so they ran a number of human subjects experiments which sought to scientifically test the different efficacy of visual encoding techniques. So this slide is one example of stimuli from their experiments. So for example, in the first example, comparing two bars in example A here, type 1, which was subjects were asked to look at two bars and then say what proportion was the smaller of the larger, and then use that as a metric to try and determine how effective the encodings were. And they did this for bars that were adjacent or separated by space, that occurred, in different charts, and also occurred at different stacking levels. So in this case, going from a position encoding to trying to compare links that are on unaligned scales. And these types of experiments were repeated for a number of different visual variables. And the result across these experiments conducted by Cleveland as well as contemporaries was to then try and put on a scientific footing some of these rank orderings I talked about earlier. And this has actually been very influential in the use of statistical graphing software, where since this work has then enabled the development of automated techniques to then use these rank orderings to search a space of possible visual encodings and then try and generate better representations as a result. Now, there's a lot of work here, and I won't be able to give it, the justice it deserves. But I will note that one important thing to keep in mind is that these different visual encoding variables aren't always orthogonal. If I can say that color works well for one thing and position for another, it doesn't always mean I can use them independently. A classic example is if I change color hue as well as color saturation or value, my perception of those is actually correlated. And so I won't pull apart two, say, separate dimensions of information from that. So there's a number of interactions that occur in our own perceptual psychology that we have to be aware of. And so I won't go into detail there, but I just wanted to highlight that fact. So getting back to Bertin, in addition to having the systematic study of visual variables, he was also an early proponent of interaction. And this is interaction even prior to computers. So this is a data table from Bertin's book, Graphics and Graphic Information Processing. Now, and this is actually data about hotel visitation for a hotel in France. So you see that basically the number of clients who are female or local from the USA, how many were businessmen, etc. Was there a convention occurring while people were there or not? So this was his initial data table, and then he wants to visualize that. So then he created a series of bar charts for each one of these variables, and in this case, the black or white is based on the value relative to the mean. So if a value was over the mean for that particular series, it was colored black. Otherwise, it was colored white to help show where high and low points might reside in the data. And then Bertin's insight was that by smartly, or intelligently reordering the data, it made certain patterns much more clear. And so he wanted the ability to interactively reorder these charts so these different trends might become more accessible. So for example, by reordering, you might see, when is occupancy the highest and what does that correlate with? Well, when there's higher occupancy, you see a higher length of stays. You're more likely to be having a convention. You're more likely to have businessmen as guests. And so in this way, you could break down the different patterns of visitation in the hotel. And Bertin was so taken with this idea of this permutation matrix, of being able to interactively reorder data to see different trends. He had a number of ingenious ways of trying to do this interactively before having a computer. So you'd print each chart out on these long strips of paper. Each one could be individually manipulated, at first by hand, as this woman being tasked to reorder the data until the patterns become clearer, to the invention of basically, a data analysis loom, which would actually be basically an early tangible user interface where people would actually physically rearrange with the help of a machine these different elements to be able to hopefully spot patterns in the data better. Now, of course, the introduction of computers has simplified this immensely, but I think it just goes to show how powerful Bertin saw interaction to be that was worth all the development of this aiding technology. And while Bertin is certainly a pioneer worth noting, I think no one is more responsible for the kind of resurgence of data graphics, at least in the United States, than the statistician John Tukey. A statistician of great stature and well respected within the community, he was actually able to speak to the community about some of its limitations, at least as he saw them. And so I'd like to read a quote from Tukey in his classic paper from the early 60s on the future of data analysis. And Tukey wrote, The last few decades have seen the rise of formal theories of statistics, quote, legitimizing variation by confining it by assumption to random sampling, often assumed to involve tightly specified distributions and restoring the appearance of security by emphasizing narrowly optimized techniques and claiming to make statements with known probabilities of error. While some of the influences of statistical theory on data analysis have been helpful, others have not. And he goes on to say, data analysis can gain much from formal statistics, but only if the connection is kept adequately loose. And so in response to the rise of formal methods in statistics, Tukey argued for basically the creation of data analysis as a separate branch, and that while there is value clearly in the generation of inferential statistics and formal methods, data analysis is much dirtier than that. And so amongst other things he invented a wider range of new graphical techniques, some of which you might be familiar, such as stem and leaf plots or the box plot, all intended to be a way to explore data prior to the process of trying to fit a model. And so Tukey strongly advocated for the separation of exploratory data analysis, where you begin to get an intuition for the shape and structure of your data, before then engaging in confirmatory data analysis, where you actually run formal statistical methods to then do hypothesis testing. And it's perhaps really focusing the attention of the American community upon this difference and the need for exploratory methods, probably one of his most lasting contributions. But Tukey did not stop there. He was also one of the early pioneers in the use of interactive techniques. But first, to illustrate some of his ideas, what Tukey was railing against was starting with raw data and then immediately trying to fit it to some known statistical model. So this is a famous example from the statistician Frederick Anscombe, which was designed to show that you can create different data sets that then you test. They have the same mean and standard deviation and are all well described or equally well described by the same linear regression. But if one takes the step of initially first plotting the data, you'll get a much clearer understanding of the different patterns that might occur, and whether or not a linear model might be correct, but with a certain amount of noise or with an outlier, or if perhaps linear models are absolutely wrong for your given data. And so with the advent of the computer, Tukey sought to take these ideas further. And one other seminal contribution he made, in contribution with others, that was done here at Stanford in the early 70s at SLAC, was the building of PRIM 9. So PRIM 9, it's an acronym that stands for picturing, rotation, isolation, and masking in 9 dimensions. And so it's a bit of a mouthful, but it's actually one of the first interactive computational systems for data analysis. And so it was built on specialty hardware and specialty software here at Stanford to allow interactive exploration of data. So I'll show you a brief clip of a film from this. So this picture here was his colleague, Jerome Friedman, who you might like to know is actually a professor of statistics here at Stanford to this day. Don't know if he still has the glasses.
He's on our block.
Okay, so he's Terry's neighbor. So just briefly, I'll show you an example here. I apologize for the grainy footage. Oops. Play this. But this is early graphics software. It's actually taking multi-dimensional data. This is 9-dimensional numerical data, projecting it down to a screen, but then enabling rotation along any of the axes of the initial data. And while in this case, almost under any 2D projection along the cardinal dimensions of the space, you just see a spherical noise. But by being able to rotate interactively within the space, they're actually able to find this interesting gash that runs straight through their data that can only be seen through a linear interpolation of different dimensions. And so this, while perhaps somewhat meager by today's standards, they actually pioneered a number of interesting ideas. So one was just the notion of interactive data analysis was quite new. Actually, I also just mentioned in passing is one of the early projects to use video rather than publications as a major way of trying to disseminate the research. So in this way, I see this as sort of the statistical data graphics equivalent of Doug Engelbart. Though perhaps with a demo not quite as exciting, still quite visionary for its time. Some of you might also be familiar with the notion of dynamic queries, of being able to interactively specify, range queries upon data. So this system had this, back in the early 70s, where you could filter along any dimension to different degrees, and this is what we referred to as isolation and masking, in addition to these rotation operators. And so this led to a renaissance of data analysis techniques, this time using the computer. And this is a screenshot from an early system from Bell Labs for brushing scatter plots. Or in this case, you'd have a scatter plot matrix. That is, you'd show scatter plots of all combinations of variables for a numerical data set, but then enable interaction to actually have interactive linking between the different charts. And this has led to modern-day statistical systems that still basically use the exact same techniques. And so amongst the statisticians, or at least some of them, gGoby is a well-known software tool, where in this case, I can drag an interactive region called the brush, and then immediately see how highlighted points in one view link across all others. In this case, the data set I'm looking at is famous data from the 1930s that R.A. Fisher used to develop the technique of linear discriminant analysis. And it's actually measurements of petal and sepals on different types of irises to see if you could statistically determine the differences between different species of flower based on these properties. And so perhaps not surprising, these different clusters you might see, for example here, it actually represents a different type of flower than the others. And so this really set the groundwork for modern-day information visualization. So this, quickly following on the heels of this was really the groundbreaking work at Xerox PARC on the information visualizer. It's like the first 3D animated workspaces showing a range of different visual representations of data. This particular one shows a hierarchical organization chart within Xerox PARC, and it's located in 3D space. And as you click different elements, the tree would rotate to bring other elements into view, and hopefully allow you to work with larger data sets than you might otherwise. And this is just one of a host of interaction techniques that were introduced by this pioneering work at PARC, including much led by Stu Card, who I'm very happy to have in the audience here. And then, others followed suit in other places. So, for example, Ben Schneiderman's group at University of Maryland also pioneered a number of these techniques and popularized a lot of the techniques we saw earlier in the work of the statisticians. So in this case, the dynamic home finder provided a technique for dynamic querying of data. So I might search for homes in different areas, in this case of Washington, D.C., by distance or by other properties. And I can interactively manipulate these different sliders to rapidly explore different areas of the data or explore different scenarios. In this case, in a way that's much more rapid than writing the underlying SQL queries that actually query the database would be. And so throughout that period, a number of different innovations occurred, and you saw a lot of consolidation in the research field. A lot of the pioneering work was published in venues such as ACM Chi and WIST, but around 95, I believe, Information Visualization Conference was established in its own right, now in partnership with the Scientific Visualization Conference. And so a number of other researchers have been engaged in the field, exploring both new graphical presentations enabled by computational technology, such as automated layout or presentation techniques, and new interaction techniques for exploring data. But I think the next milestone that occurred in this evolution is really where visualization meets the web. And so what I've shown up here is a very well-known visualization by Martin Wattenberg, the map of the market. And so this is an example of a visualization called a tree map, which here recursively bisects space to create different boxes representing different data points. In this case, showing by size the market cap for a particular company, and then by color their change in stock value. I took this image off the web last night. As you can see by the graph, it's been a rather depressing chart to look at over the last series of months. But what's interesting about this is not only that it brought interactive visualization techniques to the mainstream, but it did so on the web in a way that gathered a lot of attention. This is really one of the early examples of the visualization techniques being explored by both statisticians and HCI researchers, breaking out into mainstream use. And since this visualization was released, we've just seen more and more of this type of activity. So, for example, Google Maps was launched in 2005, which we're all familiar with, bringing panning and zooming interaction to the exploration of map data and making it really a public resource for plotting data as mashups have become more and more common. Another recent example is now, not just through services such as Google, but mainstream newspapers are now featuring interactive data graphics regularly as part of their news coverage. This is a piece called Faces of Death that allows people to explore casualties that have occurred in the Iraq War, both a timeline view with dynamic queries integrated with bar charts showing breakdowns of different statistical variables, as well as curated examples of those links along the top that correlate with specific events during the war to also help lead people through different events as they've occurred. And so what I would argue is that, this is just a few examples of a rapidly growing number of visualizations out on the web. And I think we're really at an inflection point where the results of this research are becoming mainstream in a really fascinating way. And I think also provides new opportunities for research as well. And so, in the next part of my talk, I'd like to wrap up by talking about at least 3 different research areas that I think are interesting and worth pursuing, given today's context of basically ubiquitous data, data becoming more and more available over the web in massive quantities, coupled with the rise and popularity of interactive visualizations. And so here's a motivating quote for what I'd say, leaving the modern era into perhaps the postmodern era of visualization. But Hal Varian, the famous economist, now chief economist for Google, wrote, "The ability to take data, to be able to understand it, to process it, to extract value from it, to visualize it, to communicate it, that's going to be a hugely important skill in the next decades, not only at the professional level, but even at the educational level for elementary school kids, for high school kids, for college kids. Because now we really do have essentially free and ubiquitous data. So the complementary scarce factor is the ability to understand that data and extract value from it." And so what Hal argues often, if you're looking for the place to place yourself, if you're looking for career advancement in the years to come, what was the sexy job of being computer programmer of the 90s now might move to being the data analyst is the sexy job of 2010 and beyond. And so what sort of developments can research contribute to these trends? And so I'd like to cover 3 different topics. The first being, I think there's a rich opportunity for reconciling graphical and formal methods. So we talked about the dark ages of visualization when the rise of formal statistics led to a drop in innovation in graphical methods and recent resurgence. And thanks to the computer, we can hopefully have our cake and eat it too. We can calculate in a way we never could before any number of statistical models or data mining techniques on our data, and hopefully couple that with visualization techniques that allow us not only to visualize output and understand it, but actually steer the process of formal methods and explore a space of models rather than being pigeonholed into one or the other type of analysis technique. And so I'll show you just a couple examples of footholds we're trying to establish in this area. The first, which I would actually label as a baby step in this space, is a technique we explored with a social network visualization system called Vizster. For which I had a demo running. Here it is. So as this loads, so Vizster was based on a collection of data we crawled from Friendster.com, which before MySpace and Facebook became household names, was the first social networking system to really amass millions of users. So my colleague Dana Boyd and I crawled the site and collected 1.5 million profiles, did a number of different analyses, but also built a visualization tool to allow end users to explore their own networks. In this case, you see the egocentric network from my friend Amanda, who was nice enough to let me use her data. And in this case, you see people scattered around, connected by their friendships, or at least their articulated friendships in the system, and then positioned using a force-directed layout model here. And we added a number of different analytic capabilities here, such as an X-ray mode with color encoding. So in this case, the people who are more purple are actually more popular in the larger social graph. So you can start to see who the hubs are in the larger social spheres. And were I to double-click one of these people, that network would open up and I could see the connections. And I can explore other statistical variables, such as gender, or the distribution of who's single, who's married, who's openly married, who's in a relationship. We also looked at different properties of text. So if I click the text, it actually hits a backing search index, so I can see who shares my interest in philosophy, which is smaller than those who share interest in snowboarding, perhaps not surprisingly. But the aspect that people seemed to gravitate to most was this particular feature down here, which was automated community analysis, where we ran a data mining algorithm that tried to cluster the social network in a way that maximizes linkage within cluster while minimizing linkage between the clusters. And people would, not understanding data mining per se, but were really fascinated with this technique and used it to explore intersections between different communities and differences. But because data mining techniques are not always ideal, they're maybe not always optimal, and in the case of social data, we may actually be missing important elements. We provided just this simple slider to allow people to explore the data. So for example, if I drag it all the way to the right, I actually get the connected components. So in this case, this is all the different communities, and they're separated only if they're connected only by the central actor. So basically, this is kind of the transitive closure of these different communities. Or I could drag the slider backwards and see different clusterings created by the algorithm. I could go all the way back to the left and see, basically before my algorithm has done any merges. So this way I could interactively explore the results of the data mining algorithm. We tried to pick a smart optimum based on the linkage structure, but oftentimes in user studies, people would drag this and move it back and forth until it looked right to them, and then comment, strangely enough, on how intelligent the algorithm was. And so we thought this was an interesting foothold, at least in the space of how can you interactively combine formal methods with more exploratory analysis to explore data. Obviously, in this case, it's in a playful and less analytic context, but the problem exists for more dedicated data analysis as well. So an example of that, this is a piece put together by a student I'm collaborating with, Jason Chuang, which they're running statistical NLP techniques on the collection of all dissertations produced at Stanford over the years, and then using the topic models generated by the technique, which is called latent Dirichlet allocation, to form distance measures between the different departments. And so here this is supposed to represent the distances between the different departments on Stanford campus based on topic differences in the dissertations those departments produced. So for example, I could then go back to 1993 and see things have changed a bit. But already you notice medicine kind of has its own block over here with biology close to it. For general science and engineering, the blue and the green interleave and are close to each other. And then you have social sciences and humanities over here. And as you animate over time, you might track different distances. And I'm not trying to claim that this is the optimal visualization for this data, but just to give you a sense of, you try and engaging in sense making with this data that's really heavily derived from statistical processing. And so I can move forward in time, and there's different elements we might watch. We might expect computer science and statistics to get closer together, given the rise of statistical machine learning. But I'd say point your attention to petroleum engineering, which right here is closely related to geological environmental science and geophysics, as you might expect. But as I can go forward in time, things will adapt. Still there. If I go forward in time more, you'll start to see petroleum engineering move. And so whatever's happening is petroleum engineering is now creating dissertations that have almost no correlation with any other department on campus. And so, now, the first thing I would point out is this really invites a lot of follow-up analysis. So what happened? How can we get to the source data to make sense of this trend? I think there's really interesting challenges in designing interaction techniques that allow you to move fluidly with provenance of how this data was transformed through different levels of representation. I now need to be able to drill down and understand what just happened. Is it a fluke in my data? Did I make the right choice in terms of statistical modeling? And so I think this is really poses more questions than it answers, but I think helps kind of light the way to how we might think about kind of more interactive forms of data analysis that, again, marry these statistical and interactive descriptive techniques. I'm sorry, you had a question earlier.
Do you include any budgetary or funding information in this presentation?
We could. I think the radius right now is the number of dissertations produced in that year. But you could do things with budget as well. And I think part of the important aspect of working with text, right, you have lots of metadata often associated with those texts. And so having exploratory tools that allow you to also kind of mash up the text data with other things such as budget as well will be an important component of tools going forward. So that's really supposed to be more than a teaser than anything else. We go back to the slides. There's just two other areas of research I'd like to talk about that we're actively pursuing here at Stanford. And so the other big trend I think is really interesting is that given the proliferation of data and visualizations is that graphical literacy and different types of visual expression is really on the rise. And so you see this in a number of examples. Many of you have seen Hans Rosling's talk with animated scatter plots showing you how the world's changing in terms of health and economics over time. And if you don't know what I'm talking about, go search for Hans Rosling's TED Talks. I promise you, you won't be disappointed. If you don't like data, there's sword swallowing involved. Another example is others have shown that if you communicate well enough with data graphics, it may even contribute to you gaining a Nobel Prize. But in addition to these, kind of popular uses of data graphics, people are taking them and reappropriating them in different ways. So not just to explore data, though that's common, but also to engage in maybe more comical or social forms of expression. It's probably one of the more popular examples of that. Like, people co-opting data visualization tools, to make artistic or comedic statements. And in any of these cases, that we want to ask, how do we enable the public as a whole to more effectively and quickly, efficiently create the visualizations that allow them to communicate? In other words, we don't just want to consume visualizations, we want to produce them. This is what literacy is, the ability to read and write. So how are we going to better enable that? So you can run a search on the web and ask the gurus. So let's ask Tukey. Tukey says, for the highest level of graphics, elegant, custom, expensive. I don't know why expensive is there. But enter the crunch data or the graphical output into Adobe Illustrator. This program gives complete control over typography, line weight, color, grids, layout, just what we need for doing graphical work. It is a serious, complex design program. You may want to work with a real graphical designer who will surely know their way around. Now, this would be great if I had a real graphic designer at my beck and call whenever I want. And while we can use these graphical tools to create customized static graphics, we need, I think, better tools to enable larger uptake. And so one way to do that is through programming and improving programming education. Most interactive data graphics on the web today, I'd argue, are built with Adobe Flash, and if not that, they're built with processing, an open source library which is basically the OpenGL of the new media design community. Provides an integrated development environment coupled with a simplified graphics and interaction language. And people have done this to create really remarkable and beautiful visualizations, including one of my favorites here, which is visualizations of U.S. air traffic by Aaron Koblin. However, I would argue that for everyday use, these tools, are too difficult to use. Even with programming experience, a lot of times these tools, you're basically starting from scratch in every case. What sort of higher level abstractions or semantics that people can still reasonably work with can we provide? Do we have to start tabula rasa every time? Basically, what would it mean for a typographer or a graphic designer every time they lay out a page to have to reinvent the alphabet for that particular example? And this is not to knock these tools, but just to suggest that there's a spectrum of design, and we probably want to have support at multiple levels. And so at the far extreme, people have tried to simplify the generation of graphics. This is a screen scrape from a service called Many Eyes, which is produced by IBM, which allows people to upload their data to the web, share it publicly, and then visualize the data in many ways. And so the workflow is like this. You'd first upload a data set. You might edit values, and you can view it. And then you can, from there, you click a Visualize It button, and then it would take you to a palette, so a set of templates for visualizations. So you have your data, and you have to choose a way to visualize it. And once you've done that, it then populates that visualization, and here provides a number of different slots here along the bottom, say for bubble size, label, color, that you then wire up your data variables to different visual encodings. And this is not too different from standard charting practice. In Excel is basically the same model. You have your data, pick a chart, and then you try and configure it often after the fact of picking which visualization type you want. This is often very helpful. People use this effectively because it's rather easy to use. But I tried to think, well, what's the analog? So if I think of visualization as a language, and visualizations, I'm writing statements in that language, what is this type of design akin to? And this is my conclusion, that it's Mad Libs. You're taking a template, and then you have a number of slots in which you can put in your own words or your own data, and then it will generate visualization. In this case, this is more for play, but this notion of a template as a way of designing, is very prevalent. But can we do better? Can we let people be more expressive? One approach is to consider the visualization pipeline, which is really, you can consider visualization a process of taking raw data, importing that, perhaps transforming that data, then providing visual encodings that takes that data and maps it into visual structures, then of course rendering those structures into interactive views from which you then have any number of interaction techniques then feed back into that process. And these template approaches follow this model as well. They just kind of highly structure the different parts in this pipeline. But can we break down this pipeline further into maybe more elementary operators that we can use to build custom visualizations? And a number of research projects have followed this approach. My own toolkits, which are Prefuse and Flare, follow this model. And prior to that, others have explored this. For example, in scientific computing, they have this notion of data flow programming, which you might recognize from common mashup tools on the web today. Where here on the right, you basically have a vocabulary of different building blocks that you can then wire together in different ways, often in custom ways, to create the visualization that's tailored to your particular application domain. And so if you think about this from an authoring model, you're saying, well, what is this most similar to? And the first thing that came to my mind was it's a lot like Legos. You have, have pre-structured parts that you can then put together in different ways to create novel or customized structures. The problem, however, though, is I would argue that Legos, for a number of reasons, are much more accessible than your average data flow or data pipeline tool, which often require you to learn the language and the abstractions of the tool, which may be quite different than your own thinking about the underlying domain. I might think of a visualization in terms of the graphical marks on the page, but now I have to think about it in terms of the different encoding operators I might structure together. And thus, I have a big learning curve where I learn to translate between these two different levels of representation. And so, while a number of great visualizations have been built with these tools, I again think maybe we can push, and look in new directions. So I just briefly mention a different approach that we're just starting to take here. This is work being done by my student, Mike Bostock, which is we wanted to say, how can we simplify the construction of visualizations that allow people to think in terms of the marks that are put on the page and enable this for web-based visualization. So this is a tool that's written in JavaScript currently that you can use to create visualizations for any web page embedded in there. And then the idea being that the description should be succinct enough that you could view source at any time, make the structure of your visualization transparent, and something that other people can copy, learn from, and build from. And so there's a simple model for specifying a visualization here. So you create a visualization, you specify a mark type that you want to add, in this case a bar. In this case, you're using a simple example, give it an array of data, and then I specify properties much like a style sheet. So we really drew a lot from the notion of cascading style sheets in web design here, because we know it's a successful model out in the world. In this case, you position things with respect to coordinates, such as the bottom of the bar is 10 pixels from the bottom of the canvas. You set a width. But unlike traditional style sheets, you can specify functions for doing visual encoding. So in this case, I set the height of bars, and then I set the position horizontally based on the index along the array of data. Then I can render it, and in this case, I get this simple bar chart. And this can be extended in a number of different ways. Like we might just then add new elements. We might add a rule with different data. And again, we use a very similar style of programming, in this case, I'll start adding different rules, in this case, ways to segment the data and perhaps attaching labels to these grid lines. And so we've been pretty happy with this result. There's a number of different visualizations we're able to build with this. But really, the proof is in the pudding. What expressiveness can we achieve with this style of tools? And this is still really early stage work, and we have yet to incorporate interaction. But there's a number of different visualizations we've already been able to build. So, for example, you remember the permutation matrices from Bertin that I discussed earlier. Remember coloring the cells by whether or not they're above the mean. In this case, duplicating the months. So we have a full year, and then we duplicate that data again so that we can see patterns across the winter more clearly. And we're able to specify this chart using just this couple lines of code on the right here. We set up the labels. We just set up a pane where we repeat panes for each bar chart. Again, I don't want you to follow all the code. I just want to give you a sense of how these visualizations work. We then define the bars, and then using a model very similar to cascading and cascading style sheets, I can create another copy of bars just by adding them to the original bar chart I defined here, thereby just kind of importing all the other statements I've already done, optimizing their computation, and in this case, simply offsetting the bar chart horizontally so I get this repeated structure in the graph. This is a project called ProtoVis that we're building here. It's a JavaScript visualization framework that we haven't released yet, but it's in the works. Yeah.
You heard of processing.js, right? This is equivalent of processing for JavaScript.
I'm well aware of that. And they both use the Canvas model. And so processing uses basically a low-level graphics API, so similar to Java 2D or OpenGL. And we think that's been very effective for many types of visualizations. In this case, we're taking a slightly different level of abstraction to the problem, where here you're thinking directly in terms of marks, and that will later on support interaction sort of by building in this sense of a visual object that you don't have to define from scratch yourself. So just quickly, we built a number of other classic visualizations. This is a thought called the Trellis Plot, which is invented by Bill Cleveland and others. Unfortunately, due to projection, you can't see all the details here, but there's also lines connecting here. And this is an early example of the use of computational creation of small multiples displays to explore multivariate data. And then this is still a work in progress, I think, due to some messy data. But it's just last night, so quickly, can I recreate, Minard's classic, visualization of Napoleon's March? And there's still some little design details I'd like to clean up, and our tools are under development. But in less than a half an hour, it took me about 20 minutes. I was able to reconstruct the basic framework of these classic visualizations. And so, we're going to be doing further testing with designers. Already our friends at Stamen Design are starting to play with these tools and give us feedback. But we're trying to explore the space of design of classics of graphic design to make sure our tools are expressive enough. And then later on, when we add in interaction, we'll try and take that to the next level. And so then finally, I'd like to talk about one third research area that we're exploring, both earlier in my dissertation work at Berkeley and now here at Stanford, which is what I refer to as the social life of visualization. Is that much of the research to date in the visualization has been focused on single user scenarios where you have cognitive and perceptual issues, but particularly when you get into organizations where people are passing charts around, whether it's quarterly reports, or you get on the web where you can take charts and data and distribute them widely, it's really social processes of sense-making come to the fore. And how do groups of people make sense of data together? How do they annotate? How do they deliberate and come to findings? And so we initially saw some examples of this when we deployed Vister, and we watched groups of people interact around social networks, and we found that groups of people engaged in deeper forms of analysis than individuals. We also saw an example of this on the web. So this is a visualization done by Martin Wattenberg called the Baby Name Voyager, which visualizes the popularity of baby names over 150 years. So in this case, each stack represents a name, and it's subdivided by gender, and the height of a stack is the number of people born with that name in that year. So if I start ego surfing, I'll find Jeffrey here. JE in general had a huge increase around the 1970s and 1980s before falling off. Now this was initially designed as an interactive graphic for Martin's wife's book. She wrote a book on baby names. But it quickly took on a life of its own on the internet. So for example, Martin would search on blogs and find all of these discussions of people actually engaging in exploratory data analysis of baby names. So here's one graph that a poster on a blog pointed to and said, well, look at all the names that begin with the letter A. For some reason, they died out in the 1940s and 1950s before having a resurgence. So what happened? But even more interesting, look at the letter E, and the letter I, and the letter O, and so on. The vowels used to be cool. They had a tough time, but they're fighting back. And it's not clear what's happening here. The data doesn't tell us why that's happening, but it raises some interesting questions. And I think the more interesting overarching point is that Martin Wattenberg spent hours looking at this data, both in raw form and looking at prototypes of visualizations he's making, plus playing with his own tool. He didn't find this pattern, but he put this up on the web, did a vanity search, and then soon enough, all these interesting patterns that he didn't know about were being discovered, by the crowd. And so based on these observations, we started asking some questions. The first is we just realized that, clearly visual sense making is social as well as cognitive process. And so that led us, as HCI researchers to then ask, how can user interfaces be designed to better encourage these collaborative types of analysis? And so then we sought to try and answer this question through designing, building, and deploying real systems. And so I'll give you an example of one system we built. This was a collaboration between myself and Martin Wattenberg and Fernanda Villegas at IBM. It was a system called Census. And what we did was we took 150 years of United States Census data and then tied that to interactive visualizations that were designed to support new types of collaboration around data. And so here's an example of one of those visualizations. It's called the Job Voyager. It's very similar in design to the name Voyager. But in this case, each band represents a job in the U.S. labor force. And it's, again, broken down by gender. And right now it's normalized, so you see percentage within each year. So, for example, you'll see the huge collection of farmers, which then has died out over the years. So what happened to the poor farmers? And we can zoom in, and as we do so, we see someone's left a comment behind. In this case, the commenter says, "There's no arbitrary division of labor between men and women on a farm. Unless there are millions of bachelor farmers, these numbers have more to do with the prejudices of the folks in charge of the data than with the populations of American farms. So this guy has a bone to pick with the Census Bureau, and he feels that women are being underrepresented, that they are contributing to the work on the farm, but perhaps due to how head of household is defined, that men are dominating this chart. And so this is one of the patterns that we see where people actually engage in data integrity issues as they explore data. And there's other examples as well. We could filter, for example, by gender, and we'll see a large influx of women into the labor force after World War II. And this led to some discussion, in this case people also annotating the chart to make it clear what they're talking about. Someone else notes that, well, look, household worker had the opposite trend. So in this way, people can both point and talk about different things in the display. You can also search the data by typing in keywords. So here's the letter B. So it's all jobs that have a word that begin with the letter B. I'll keep typing. You can watch the location bar along the top here. Type in BA. Get all jobs that begin with BA. BAR. And you see this updates in real time on the location bar. And while perhaps a relatively minor design issue in some sense, it's actually crucial for supporting collaboration in that any moment I can copy and paste what's there, put it in an instant message, email, or blog post, and the other person can come and see the exact same thing that I was seeing. That's helping establish the common ground necessary for a meaningful dialogue about the data. And here's the URL that I would email, because I find this one particularly interesting, which is, no one will admit to being a bartender in 1930. Perhaps not surprising. So we have other examples of charts that look like this, and they're called missing data. This one I don't believe is. And people are very good at teasing that apart and helping others interpret the data as such. Then we notice, for example, there's a rise of women as bartenders subsequent to that. There's a few other examples. One really popular view is the military, which has a very dramatic picture of a Cold War buildup. This led people to engage in different conversations and begin to annotate the chart with different timelines and discuss this. One of the things I'll note, though, is I typed in MILI as my query. If I click the chart, I actually changed my query to military with a capital M. It's important, though, that I still get the same text back. I mean, the insight here is that the parameters of the visualization might still lead you to the same view. So to make sure people don't miss out on conversation, we actually index the result set for any view to make sure that the right collaborative commentary is accessible to folks. And then one other example I'll show you is waiters. And the reason I like this example is because, among other things, it shows a weakness in the type of visual representation we picked. This was a prototype research system. In an ideal world, you'd actually be able to look at the data in many different ways. And that's what I would do if I was releasing this into the wild as a commercial tool. Because in this case, the stacks can bias perception of each other. So given the big uptick here in female waiters, you might not see what's actually happening with male waiters at the same time. So for example, if I zoom in on just men, you see there's actually a huge dip in the late half of the 1900s. So this is interesting enough maybe to warrant a comment. So I could say, why the dip in males? And then I might, be conscientious, point to what I'm talking about. Anyone have any hypotheses on why males may have dipped? That is the late 1900s, so it's from 1940 is the peak here to 1960 to 2000.
War for a little bit of that.
So there's World War II, Korean War, Vietnam War, right? What's that?
GI Bill.
So I guess the GI Bill, people going to school instead. Any other theories?
Manufacturing.
What's that? Manufacturing, yeah, there might be a growth in manufacturing jobs.
Relabeling.
Oh, relabeling. So you could have a change in schema, or basically a change of categorization. One other possibility that has been suggested to me by social scientists is what they called feminization, which is that large rise in women may actually have been a cause for having less men. That could be due to wage disparity, but also to how the occupation is perceived. So anyway, we can save this question and maybe leave it for someone else to try and answer. So we submit the comment, it's here. Maybe I'll want to revisit it later. So I can actually collect views to create tours through multiple views. So for example, I might come back here and post a signpost for someone else. Say, don't miss the dip in males. Here. And then if I want to, I can drag and drop these links, for example. So it's in here, save the comment, and then other people could come and see what I was talking about. So for example, I might follow this up and then ask, well, can I test the theory that it had to do with war? So I might, create a query where I combine it with military and then look at the difference. And, this is not the best plot for seeing it, but you will see that, the peaks in military tend to coincide with the lowest dips in waiters, so that might be a factor in this particular case. And then one final example is just in addition to the visualization, people could explore commentary. So I could look at different comments left by others. I could search over it. And I'm new here at Stanford. This is my first quarter, so I probably should learn about disappearing professors. I don't know if Scott and Terry have any insights into this. And so in this case, sorry for the reload, you see that there used to be, for a number of years, subdivisions of professor into different subcategories. But due to changes in schematization, this commenter points out that now all professors are in this general category. So again, with real-world data, you also have messiness, whether it's in terms of needed data cleaning or changing schemas. And we found that people's collaborative commentary actually help make sense of this and help others interpret the data more successfully. And since we released this system, we ran studies of it. And then subsequently, my colleagues at IBM released another site that I mentioned earlier, Many Eyes, which allows people to upload data, tie it to visualizations, and then engage in commentary around those visualizations. And so some of the different patterns of usage we see on these sites, here's an example from Census where a comment pointed out, why is there a peak in dentistry in 1930? Like, there's male dentists. And bartenders called themselves. Yeah, maybe that's what bartenders called themselves. That's a good theory. We'll have to try it out. And so, strangely enough, I didn't expect this. This actually led to a lot of conversation. So someone said, well, we started adding fluoride to the water, so maybe we didn't need as many dentists. But what's with that bump? And so then people started giving personal anecdotes. I went to the dentist once a year, but my kids go twice a year. Maybe that has something. It's all a scam. But then other people said, well, let's look at the data. What does the data tell us about the data? So they zoomed out and said, well, dentists drop, but technicians, like medical and dental technicians, are skyrocketing. So maybe what we're seeing is a stratification of the labor force. So dentists is becoming more high profile, and they have, a class of laborers working with them. Skilled laborers, obviously. And then people tried to back that up by going out on the web and looking up salary statistics and seeing if that was confirmed. And so in this way, people kind of iteratively made sense of data by building on top of each other's commentary. And we've seen this in different domains too. Since we released this system, not only has Many Eyes been released, but a number of commercial business intelligence vendors have been releasing server-side products as well that enable collaboration. So here's an example from a tool called Tableau. This is a graphic from Microsoft's Xbox group where you have designers building games, and then you have testers who are running play tests with these games, collecting rich statistics from those play tests and visualizing them to share with the game designers. So here's what they call, in this particular instance, the Valley of Death. So this is a first-person shooter where people are running in and then they're dying in there. And this is actually really important because the designer said, well, I want my perfect shade of red. Because if it's too red, then it means people are dying all the time, and it's no fun. And if it's not red enough, then it means they're not dying at all, and it's also not fun. So there's actually this conversation between the game designers and the play testers where they're creating visualizations, and then they're collaboratively discussing it, and then changing the game design, and then reiterating on the play tests. And so this way, visualizations are helping make the decisions of how to design that game.
What's the axis?
The axis here is, this is just coordinates in Game World. So this is this is a terrain map of the virtual game world. Sorry, and then the red dots are number of deaths in that cell. And then one final example, this is from Many Eyes, where people have been discussing, in this case, carbon dioxide data. And so someone posted a graph of CO2 over time, and it also had, other data elements into it. So CO2 levels, temperature, time. And so people started picking apart this data and discussing it in different ways because there's passions flaring on both sides of the issues. And so people changed the chart from, say, a time chart to something else. So in this case, trying to look at correlation between temperature and time. You have this scattering of data and this really weird trail here. That's actually where the person integrated two different data sets. And so it seems like, the quality of measurements may have changed, over different years. So that's actually segmented by year. So people tried to make that clearer by coloring with a year threshold, and they got this to break it apart. And this led into a big discussion of how the data was processed, to the point where the person who joined the data together, he had actually taken temperature data and CO2 data from different sources and realized he had done so in error, so there was an offset between data that was incorrect. And so by the crowd picking this apart actually led the person to retitle his chart Flawed Data, then reran his analysis and posted a new visualization elsewhere on the site. And so these are just some of the examples of the ways in which collaboration can help make sense of data. But I'd argue that this sort of research is still in its infancy. How can we better support data analysis processes collaboratively? And so we might get some insights from how people actually have used these systems. We ran a content analysis of commentary, where basically we went through and labeled the different roles comments play. So these are non-exclusive labels that might be applied across these different services. So in both Census and Many Eyes, we found that, not surprisingly, the most common contributions are questions, observations, and hypotheses about the data. And typical questions and hypotheses are more likely to spark further discussion. Interestingly enough, another really highly prominent activity was people engaging in data integrity issues. So whether it's data cleaning, pointing out faulty values, and oftentimes wanting to change the data or help clean it up, but being limited by the set of tools. So it's interesting to think about how we might further enable interaction with the underlying data. And then finally, one qualitative result that we found was what we called voyagers and voyeurs, which was complementary phases of analysis. So people might have been voyagers. They all started off that way, where they were searching the data within the visualization, looking for patterns in census. And eventually, everyone tired of this. They either ran out of questions, such as they'd already searched for their jobs, their mom's job, their dad's job, their brother's job, their friend's job, and then went to the comments to see what else people were searching for. And we called this voyeur, and this came from one of our participants who said, "I feel like a data voyeur. I love seeing what other people have been searching for." And so in this way, people would actually sometimes play armchair psychologists and guess what their colleagues would find interesting. But in all cases, actually came across new topics of interest to them, which then sparked them to going back into the data analysis process. And this, by surfacing social activity, we actually saw this feedback loop in how people explored the information. And so I think just to conclude, I think there's lots of different ways we might follow up on this research and better enable the social life of visualizations. And that might include how people collaboratively manage data, whether it's through data integration techniques, cleaning. How can we crowdsource the ways that we deal with data on the web, particularly given how much of everyday data and everyday people are now getting engaged, not just elite data analysts. How people might contribute to visual mappings and visualizations directly. Our work in ProtoVis is one way we're trying to simplify visualization creation so that more people can participate in this way. And then finally, we can more deeply look at aspects of visual analytics. So how do people explore data? How do they engage in sense making around data? And how can interfaces better support that? And then again, I think we should take this model of visualization I proposed earlier and really think about it a little more holistically, including feedbacking through the entire process, and not just with a single individual, but with groups of people perhaps contributing at every point along the way. And so with that, I'll just conclude by saying that this is really all in service of a larger goal of sense-making. This is a chart taken from Stu Card's book on visualization and sense-making, where really it's not just about working with visualizations. It's about people trying to understand data, to answer questions. How do they search for data? How do they find it? How do they organize it? How can that be shared? How do then they organize that data, create visualizations of it, really engage in comparison and problem solving. And then what actions do people take? So how can people better disseminate their findings? How can that lead to iteration, where you go back into other parts of this loop? And how does it support decision making, both in individual and social contexts? And so obviously it's a wide range of things, and given that I'm out of time, I won't go into further detail, but just to say that I think there's many interesting research topics in HCI that this work in visualization exposes, and I'm really excited to continue to pursue them here at Stanford. So with that, I'd like to thank you for your time and take any questions you might have. Yeah.
In assume that you collect data on people that are using your tools and visualize how it is.
Yes, so I didn't show examples of that, but there's what we call meta visualization, which would be, and we've done some examples of this in research. Is what we did was we took people's visitation patterns and commenting patterns across different sites, then took that data and put it back into navigation widgets, so that as people explored the visualization, they actually had visual cues of where people have been and where they hadn't been. And what we found was that, not surprisingly, surfacing that data, people preferentially navigated to popular or controversial views more likely. But also by being able to see where people hadn't been, we actually got more unique discoveries, so that when we gave people hypotheses and asked them to track down either evidence for or against, they could preferentially navigate to the views where other people's hadn't been, and then thus kind of encourage broader coverage of the data. And so that was just kind of a small foray into that area. I think making the community's data visible to the community itself is also kind of interesting. And once you have this sort of recursive, a reflective system, I'm really excited to see what will happen. Yes?
Has anyone done any work on, I guess, tools that would suggest suspect data? I mean, visualization.
Right. That's a great question. And so basically, are there tools that will suggest kind of suspect or interesting data? There's certainly techniques for outlier detection. And other examples is that. I think by knowing what data slices people are looking at, you could actually implicitly do steering of data mining on the back end. And this is a little bit out of my area of expertise. I'm still building up more of my knowledge in the data mining area. But I think it's a nice bullet within the space of kind of combining both formal methods and exploratory methods in data analysis, and understanding how the computer for data analysis can be not just the creator, kind of medium for visualizations and social communication, but you can actually leverage computation, on the back end to help people find interesting patterns. So the short answer is I haven't done it, but I think it's a really important and interesting area for future work.
If you were intrigued by recovery.gov and if you're going to look at their data and try to visualize.
Right. So when I look at recovery.gov, I've been keeping my eye on it, and as I see how their data APIs progress, I'd very much love to start to visualize that data, and I'd be happy to contribute to the new administration. were I so asked. Yeah. Bjorn.
Yeah. So. One thing that struck me in the Halvarian quote that you had was that there was an underlying assumption that the data is pre-existing, it's already out there. And I was wondering if you could speculate on how both visualization and interaction techniques may be the same or different if actually eliciting the data is part of your task. So examples are, if I take an oscilloscope and I'm debugging a circuit, or if I'm debugging a program that I'm writing, then I can actually generate new data on the fly as well.
So this is a great point. The question is, the Halvarian quote maybe had an assumption that there's all this data being generated and there's sort of almost like a waterfall, right, of data through analysis. But really, data generation occurs all along the way. You're exactly right. And we've looked at this in some ways. So one is, just by doing analysis, your actions, your activities, we mentioned, is another form of data. And we've actually done history visualizations where you see the provenance of your own analytic session. Other examples include collaboratively authored data sites like Wikipedia or Freebase, where you might actually create a visualization of data stored in these services, but then see missing data and actually be able to contribute to the database through the visualization as an interface. I think there's a lot of great examples where we can think about how we generate data. One other example I'll briefly mention is on Many Eyes, people posted a visualization of the most popular holdings of U.S. libraries. And all the Harry Potter books were like huge circles in the center of this diagram, most popular, and there's all these others. And then what people did was they went through and they just clicked all the examples of the books they've read and then saved it as a comment. And then 30 other people followed suit. So you basically had people voting on all the books they read. Now you would like to be able to have this data in a relational format where you can visualize it and actually get a sense of community reading patterns. In this case, all that data was trapped in the selection vectors for that individual interface. But it really suggests interesting ways in which data visualizations don't just share data, but they might entice us to provide more data. I have colleagues who use, actually both at Intel and elsewhere, are actually using visualizations as probes as they do qualitative interviews as well. So I think the evocative nature of visualization is something that these social approaches to visualization we really could leverage to great effect. Thanks for the question. Yes?
So you said that on the web that data is becoming ubiquitous and free?
Mm-hmm. Not in all cases.
Okay. Yeah, it's going down. It's not all the same quality. It's not all high quality. It's all not even There's no XML data. Sure. There's no Google. You can't say, find me an interesting data set with these includes variables that is 5 clusters or something.
Actually, if you look at work by Mike Caffarella and Alon Halevi, that's actually not completely accurate. They actually have systems now that are crawling all the text tables on the web, identifying which ones have relational data and enabling search over that. It's not been released, but it's been published at VLDB. So Google is on the way with that. But I think the underlying point that you are getting to, like, do I trust that data? What's its quality? I think, is something that's going to have to be, if you can have, political or legal or other things that basically stamps of approval that will help. I think there's lots of different ways to do it. Some of that is just going to have to be social as well. I mean, it's one of these like thorny and I think interesting HCI problems that's not purely technical, it's not purely political or legal, it's also social as well. And I think one technological aspect that we can help support to encourage that is, being able to visualize and explore the full chain of provenance. So when I get into the case where I have techniques for integrating data from multiple sources, the ability to backtrack and follow that will at least help somewhat in helping people make sense of the data for themselves. But I don't, I think there's many more questions here than there are answers, but I also see it as a research opportunity going forward. Well, I think that the data will be ubiquitous. The question is, we'll probably have the ability to select from multiple sources and have metadata about those sources. So I don't know yet. It will remain to be seen what the usage of that data will be. Certainly it will be available. Yes?
So I'm just thinking of the different subfields that are out there, like information visualization, scientific visualization, photography, geovisualization. Do you think that's more just a reflection of the history of research communities, or maybe something more meaningful, like levels of abstraction, or which geometries you use in your...
Yeah, it's a classic question in visualization, particularly from when I talk with people who are outside but familiar enough to know, what's the deal with InfoVis versus SciVis versus GeoVis? Can't you guys get along? Well, the truth is that there's a number of reasons for it, some of which are kind of rooted in the material. For example, but I think a lot of that also comes out of just historical precedent. I mean, the SciVis community largely came out of scientific computing and 3D computer graphics. The InfoVis community came out of cognitive science and human-computer interaction, with the user interface focus. Whereas GeoVis, I think cartographers are a special case because I think they have the longest and richest tradition of any of these visual representation of data disciplines. The good news is that I think they're all talking to each other. There are technical differences. SciVis tends to deal with data that has a given spatial layout. It doesn't mean you can't abstract it. But in general, InfoVis kind of says, well, we do work where we design the layout, where SciVis does work where the layout's given. I think those boundaries are somewhat false. I mean, the closer you get to the boundary, it gets fuzzier and fuzzier. But all these different communities are beginning to talk to each other more and more. The visualization conferences are now co-hosted. And so I think while there's very cultural differences that have emerged given the source disciplines that many people come from, going forward I think those lines will blur more. And I think another force pushing that is that you're also having more and more interaction designers who aren't necessarily associated with any of these research fields also getting involved. And so there's a lot of crosstalk and learning that I think we will all benefit from. So hopefully that answers the question. Okay, well I think I'm out of time. So I'm happy to take any more questions you have offline.